When you look at NASA's current plans for returning to the Moon, it's hard not to feel like we've made things unnecessarily complicated. Multiple rocket launches, orbital refueling stations, spacecraft rendezvous in deep space, and complex lunar orbits. Sometimes you just want to ask, why can't we simply launch one rocket and fly straight to the Moon? Here's the surprising part. That idea not only existed in the 1960s, but it might actually be possible today, with some clever modifications to SpaceX's Starship. Welcome to the concept of Nova Starship, a fascinating fusion of vintage space-age ambition and cutting-edge rocket technology. To understand why Nova Starship is interesting, we need to look back at how we've gone to the Moon before. NASA's Apollo program used a method called Lunar Orbit Rendezvous, and it was brilliantly efficient for its time. The approach was elegant in its division of labor. The combined Apollo spacecraft would enter orbit about 100 kilometers above the Moon's surface. Then it would split apart. The lunar module descended to land, while the command module stayed in orbit with one astronaut aboard. After surface operations, the lunar module's upper stage would lift off and dock with the command module within a few hours. The crew would transfer back and head home, leaving the lunar module behind in space. This method worked flawlessly from Apollo 11 in July 1969 through Apollo 17 in 1972. The genius of Lunar Orbit Rendezvous was efficiency. You didn't need to land your entire spacecraft on the Moon and haul it back off again, which saved enormous amounts of fuel. Fast forward to today's Artemis program, and NASA is using a similar approach, but with significantly more complexity. Astronauts will launch on the Space Launch System rocket aboard the Orion capsule, travel to lunar orbit, and transfer to a separate lander, just like Apollo. But here's where things get complicated. NASA has selected a modified version of SpaceX's Starship as the lunar lander, called Starship HLS. Unlike Apollo's lunar module, this Starship will launch separately and uncrewed. Before it can even head to the Moon, it needs to be refueled in Earth orbit by tanker versions of Starship, and this could take anywhere from 4 to 12 separate launches. The payoff for all this complexity? Starship could carry over 100 tons of cargo to the Moon and back, far exceeding Apollo's capabilities. But the downsides are significant. The program is incredibly expensive, operationally complex, and depends on multiple systems still under development that have already experienced delays. Back in the 1960s, NASA and Soviet engineers studied several different approaches to lunar missions. One concept stood out for its straightforward simplicity: direct ascent. The name says it all. In a direct ascent mission, one massive spacecraft launches from Earth, flies straight to the Moon, lands, takes off, and returns home, all without assembling parts in orbit, waiting in parking orbits, or docking with other spacecraft. Everything happens in one continuous mission using one vehicle. It sounds almost too simple to be true. And there was a catch. It required an absolutely enormous rocket. To make direct ascent possible, NASA designed a super heavy rocket called Nova. The most powerful version, the Nova 8L, would have used 8 F1 engines in its first stage, the same engines that powered the Saturn V, but with 50% more of them. This beast could have sent approximately 68 tons directly toward the Moon. Various Nova designs explored different configurations, including solid rocket boosters and even nuclear engines in the upper stages, with payload capacities ranging from 48 to 75 tons. Despite its impressive capabilities, Nova never left the drawing board. In 1961, NASA chose Lunar Orbit Rendezvous instead, which meant a smaller rocket could do the job. The Saturn V was selected over Nova, and interestingly, raw performance wasn't the deciding factor. The Saturn V could be built using an existing factory near New Orleans, the Michoud assembly facility. Nova, on the other hand, was so wide it would have required constructing entirely new factories. It's not exactly an epic reason to cancel what might have been the most powerful rocket of its era, but sometimes history comes down to logistics and budgets. For Apollo's goals, landing humans on the Moon and returning them safely, Saturn V was absolutely the right choice. It worked, It was, relatively, affordable, and it accomplished the mission. But today's ambitions are far more expansive. NASA envisions permanent moon bases, long-term infrastructure, and possibly nuclear power systems on the lunar surface. All of this requires moving far more mass than Apollo ever did, mass levels much closer to what Nova was designed to handle. And here's where things get interesting. We may already have a modern equivalent. SpaceX's Starship shares remarkable similarities with the Nova concept, especially in raw power. Starship's first stage, Super Heavy, uses 33 Raptor engines producing up to 73.5 meganewtons of thrust, significantly more than Nova's first stage. Its upper stage, powered by 6 Raptors, also exceeds Nova's upper stage in thrust capability. There are differences, of course. Starship's engines have lower specific impulse than Nova's, though the vacuum-optimized Raptors narrow that gap. Starship's dry weight is also higher than Nova's upper stage, but for lunar missions, Starship would remove heat shields and other Earth return hardware, significantly reducing its mass. If SpaceX wanted to push this concept further, they could theoretically revisit carbon fiber structures, as originally planned for Starship, to cut weight even more, though at considerably higher cost. Adapting Starship into a Nova-like vehicle would require several major changes. The biggest shift involves how Starship uses its fuel. Currently, Starship is designed for full reusability, always reserving propellant for landing back on Earth. For a true direct ascent moon mission without refueling, it would need to burn nearly all its fuel just to reach the moon. One intriguing possibility is adding a third stage, similar to Nova's original design. This is surprisingly practical. Starship's cargo bay is massive, capable of carrying over 100 tons. That provides plenty of room to integrate an additional stage inside the vehicle. This internal stage could provide the final push for direct lunar injection or deliver extremely heavy payloads to the moon without major structural changes. According to research from NASA's Johnson Space Center, a direct ascent mission would work like this. The spacecraft launches straight from Earth toward the moon in one continuous push, reaching Earth escape velocity of about 11.2 kilometers per second. It then coasts for roughly 3 days, making a few small course corrections to fine-tune its path. As it approaches the moon, at over 1.6 kilometers per second, there's no atmosphere to slow it down. Instead, the spacecraft begins powered descent at around 15 kilometers above the surface, firing engines to cancel all that speed and gently touch down. A complete round-trip mission requires about 15 to 16 kilometers per second of total delta V, with roughly 5.5 to 6 kilometers per second needed just for landing and takeoff. This elegant simplicity comes with brutal technical demands. Because of the rocket equation, even small increases in vehicle mass require large increases in fuel. That's why direct ascent is both conceptually simple and practically demanding. One significant issue is Starship's construction material. The stainless steel design, while resilient and cost-effective, adds considerable weight compared to Nova's aluminum construction. Nova's empty weight was just over 258,000 kilograms, while Starship weighs approximately 300,000 kilograms empty. That's 50 metric tons of additional mass. The original carbon fiber design for Starship would have been lighter but dramatically more expensive to manufacture. Another consideration is fuel choice. Starship runs on methane and liquid oxygen, which works beautifully for Mars missions where in-situ methane production is feasible. But on the Moon, there's virtually no methane available. Traditional upper stages use hydrogen and oxygen, both of which can potentially be manufactured from lunar ice. This is why some experts suggest a third stage using hydrogen-oxygen engines might be more practical for sustained lunar operations. Despite the challenges, a Nova-style Starship offers compelling advantages over current plans. Simplified operations eliminate the need for 4 to 12 refueling launches before every moon mission. This dramatically reduces operational complexity and launch cadence requirements. Reusability, where it matters. Unlike the original expendable Nova, a Nova Starship could reuse its first and second stages, returning them to Earth while potentially leaving the third stage on the Moon or in lunar orbit for future missions. Reduced environmental impact. Fewer launches mean less disruption at spaceports. As we've seen at Boca Chica, local opposition to frequent Starship launches is already significant. Launching 11 times for every lunar mission would intensify these concerns. Greater payload capacity. Nova was theoretically capable of delivering 68 metric tons to trans-lunar injection, 30 tons more than NASA's SLS. A properly configured Nova Starship could potentially match or exceed this capability. Future-proofing. With nuclear thermal engines being tested by NASA for potential use by 2027, a third-stage slot provides a natural upgrade path for even more ambitious missions. Before we get too excited, there are significant reasons why this approach hasn't been immediately adopted. Development costs. Modifying Starship for this mission profile would require substantial investment. Carbon fiber construction, while lighter, would be extremely expensive. Developing and integrating a third stage adds complexity and cost. Unproven technology. While individual components exist, the complete system has never been tested. Direct ascent missions have never been attempted by humans. There's a reason Apollo chose lunar orbit rendezvous. Delta-V limitations. Current Starship configurations struggle with the Delta-V requirements for complete lunar round trips without refueling. One reason experts discuss leaving Starships on the lunar surface as habitats is because they may lack sufficient fuel to return to Earth after landing. Single point of failure. With everything riding on one launch, one vehicle, there's less redundancy than multi-launch architectures provide. If something goes wrong, the entire mission is lost. Propellant optimization. The challenge of reserving zero propellant for landing, making the vehicle expendable, versus maintaining reusability creates difficult engineering trade-offs. For decades, scientists have understood something most people still overlook. Space isn't just empty, it's the most powerful energy environment we have access to. Even Elon Musk has pointed out that space-based industries, especially orbital solar power, could one day be worth more than Earth's entire economy combined. That may sound extreme until you look at the numbers. By 2050, space-based solar power alone is projected to supply up to 80% of Europe's renewable energy needs. The reason is simple and hard to ignore. Space receives roughly 100,000 times more usable solar energy than Earth's surface, while still tapping less than 1/millionth of the Sun's total output. We're not running out of energy, we're just standing in the wrong place to collect it. This is where space-based solar power changes the equation. Its real advantage isn't just that it's clean. It's that it delivers energy continuously, predictably, and at scale, something Earth-based renewables still struggle to do. Traditional solar panels stop working at night. Clouds reduce output. Weather creates instability. Space-based solar doesn't have those problems. Satellites placed in geostationary orbit remain in near constant sunlight, producing power 24 hours a day. That consistency matters. Because of its stability, space-based solar power can function as true baseload energy, directly competing with nuclear and fossil fuels, not just supplementing them like wind or ground-based solar. There are no sudden drops from storms, no regional blackouts caused by weather systems moving through. And the efficiency is even more striking. Outside Earth's atmosphere, solar radiation isn't scattered or absorbed. Energy intensity is about 1.5 times higher than the absolute maximum possible on the ground. Solar panels in space can also stay perfectly aligned with the sun throughout the day, capturing energy at peak efficiency without interruption. In practical terms, a single large satellite could generate up to 2 gigawatts of power, enough to supply millions of homes. But power generation is only part of the story. What makes this system truly different is flexibility. Instead of being locked to one location, the energy transmitted via microwave or laser can be redirected to wherever it's needed most. power could shift between regions based on time zones and peak demand. Remote research stations, disaster zones, and areas without stable grid infrastructure could receive energy on demand. Space-based solar can even power other spacecraft, reducing launch weight and extending mission lifespans. And looking further ahead, this technology isn't just about Earth. It's one of the most realistic solutions for providing continuous energy to future bases on the Moon or Mars. At its core, space-based solar power works in a surprisingly straightforward way: collect sunlight in space, then send that energy back to Earth wirelessly. There are three main steps, and once you see them, the concept clicks. First is energy collection in space. Massive satellites, some over 1.5 kilometers wide, are placed in geostationary orbit roughly 36,000 kilometers above Earth. From that position, they stay fixed relative to the ground and remain almost constantly exposed to sunlight. Using large solar arrays or reflective mirrors, these satellites harvest solar energy without interruption. Next comes wireless energy transmission. The electricity generated on board isn't sent down through cables. Instead, it's converted into microwaves or laser beams. That energy is then precisely directed toward a specific location on Earth, passing safely through the atmosphere. The final step happens on the ground. A large receiving station known as a rectenna captures the incoming energy beam. These rectennas can span several kilometers, and their job is to convert the microwaves or laser energy back into usable electricity. From there, the power flows directly into the national grid like any other energy source. This process reveals another major advantage that's easy to miss: land use. Because space-based solar collects sunlight non-stop day and night without clouds or weather, it's dramatically more efficient than ground-based solar. Estimates suggest it can be 5 to 10 times more productive. That efficiency means far less land is needed on Earth. A space-based solar power plant might require only 1 to 2 square kilometers of receiving area compared to 20 to 50 square kilometers of traditional solar panels to generate the same amount of power. So, beyond clean energy and constant output, space-based solar quietly solves one of renewable energy's biggest constraints: space itself. Despite all of this promise, space-based solar power still faces real skepticism, and most of it comes down to cost. Launching enormous structures into space has always been brutally expensive. Right now, that's the biggest obstacle standing between SBSP and large-scale deployment. Multiple studies agree on this point. A 2020 UK government feasibility study estimated that building, launching, and maintaining satellites capable of delivering 2 gigawatts of power would cost around £4 billion. At today's prices, that makes SBSP hard to justify. But that conclusion assumes yesterday's launch technology. The entire cost equation starts to change with fully reusable rockets, especially SpaceX's Starship. To understand why, consider the scale involved. A single SBSP satellite with a diameter of about 1.5 kilometers would cover more than 1.8 square kilometers and weigh thousands of metric tons. No rocket, including Starship, can launch something like that in one piece to geostationary orbit. That's not the plan. What Starship enables is something that legacy rockets never could: affordable, high-frequency, multi-launch construction in space. Starship is designed to carry roughly 100 to 150 plus tons to low Earth orbit per flight, around 20 to 30 tons directly to geostationary orbit, and potentially more than 200 tons in future versions. On its own, that's impressive. But the real breakthrough is reuse. Once both the booster and the spacecraft are fully reusable, launch costs could drop from billions per mission to potentially under $10 million per flight. That's not a small improvement. It's a collapse in cost. The price per ton to orbit could fall by 100 times, 1,000 times or more compared to older rockets. Even more important is cadence. Starship isn't designed to fly once or twice a year. It's built for rapid reuse, dozens, then hundreds, and eventually thousands of launches annually. That kind of launch rate makes it realistic to deliver enormous amounts of material into orbit every year. And that's the missing piece. With enough launches, massive SBSP systems don't need to be launched whole. They can be assembled step by step in space, the same way large structures are built on Earth, just at orbital scale. Beyond giant power stations like space-based solar power, Elon Musk has pointed to a second, quieter shift happening at the same time moving computation itself into space. According to Musk, Starship should eventually be able to place around 300 gigawatts per year of solar-powered AI satellites into orbit, and possibly closer to 500 gigawatts. These wouldn't be traditional satellites. They'd be compact orbital data centers running AI computation non-stop on constant sunlight. No batteries, no downtime, just continuous power and cooling in space. This idea surfaced in response to a post by Salesforce CEO Mark Benioff, who made a blunt observation. The cheapest place to run data centers may ultimately be space, where you have uninterrupted solar energy and don't need massive battery systems or terrestrial cooling. Musk added an important comparison. On average, total U.S. electricity consumption sits around 500 gigawatts. That estimate lines up with public data. In 2024, the U.S. generated about 4,151 terawatt-hours of electricity, which averages to roughly 473 gigawatts across the year. Put those numbers together, and something striking emerges. At 300 gigawatts per year, in just 2 years, orbital AI systems could match or exceed the total electrical power used by the entire United States. And it doesn't stop there. Every year, more capacity gets added. The curve compounds fast. What makes this plausible is scale. Humanity already manufactures more than 1,500 gigawatts of solar panels per year on Earth, far more than what these early orbital systems would require. As Musk put it, Starship's role is to solve the tonnage-to-orbit problem. Once mass can be moved cheaply and repeatedly, power generation is no longer the bottleneck. The real constraint becomes something else entirely: chips. AI systems need enormous numbers of processors, the tiny brains inside computers. That's why Tesla is building a massive chip manufacturing facility known as the Tesla Terafab. The goal isn't just better chips, but producing them fast enough to keep up with orbital deployment. Even then, this vision is still modest compared to what comes next. All of this points toward a much larger concept often associated with science fiction: a Dyson swarm. Instead of a single structure, it's a vast collection of satellites and solar collectors orbiting a star, capturing a significant fraction of its energy output. For a sun-like star that's on the order of 10 to the power of 26 watts, the defining threshold of a Type II civilization on the Kardashev scale. Reaching that level would likely require moving manufacturing off Earth entirely. Musk has suggested a long-term path that starts on the Moon. Robotic factories could mine lunar regolith for silicon metals and oxygen, then mass-produce satellites equipped with solar arrays and AI hardware. Instead of rockets finished, satellites could be launched using kilometer-long electromagnetic railguns, mass drivers that fling payloads into space at escape velocity, dramatically reducing cost. Seen this way, orbital AI data centers aren't the end goal. They're the early practical steps toward an energy-rich civilization that no longer depends on a single planet to power its intelligence. That concern didn't appear out of nowhere. During Artemis 1 in 2022, Orion re-entered Earth's atmosphere and splashed down safely. Publicly, the mission was declared a success. But once the capsule was recovered, engineers noticed something they hadn't expected. The heat shield wasn't worn smooth and evenly as ablative systems are designed to be. Instead, it was pockmarked, marked by deep divots, where chunks of material had broken off entirely. NASA described this as char loss, the normal shedding of material during re-entry. What the hardware showed was something far less ordinary. Char loss is gradual. It happens evenly as heat burns material away. This wasn't that. Large fragments had separated from the surface, leaving behind cavities in the protective layer. Whatever term was used publicly, the damage pointed to a different physical process, one that wasn't part of the original design assumptions. NASA didn't release images of the damage until months after the mission ended, and the full Inspector General report didn't arrive until 2024. By then, the technical explanation was already becoming clear. After months of analysis and testing in high-temperature arc jet facilities, NASA identified the underlying cause. The Avcoat heat shield used on Artemis 1 was too impermeable. In simpler terms, it couldn't breathe. As Orion plunged into the atmosphere at speeds exceeding Mach 30 surface temperatures, climbed toward 2,700 degrees Celsius. That heat didn't just burn material away, it generated gases inside the heat shield itself. In a properly behaving system, those gases escape gradually. In this case, they couldn't. Pressure built up beneath the surface, stressing the material until cracks formed and sections fractured away. Despite this, flight data showed something reassuring. Temperatures beneath the heat shield never exceeded about 160 degrees Fahrenheit, well below the composite structure's tolerance limit of 500 degrees Fahrenheit. Beneath the Avcoat sits a strong composite shell supported by a titanium framework. The National Space Agency ran internal what-if-we're-wrong tests. Even assuming significant heat shield loss, the structure still protected the capsule and allowed for a survivable landing. From NASA's perspective, that margin mattered. It's also the reasoning that led to the most controversial decision of all. Rather than replace Artemis 2's heat shield, a process that would have been costly and delayed the program, NASA chose to fly it as is. Instead, they adjusted the mission profile. For Artemis 2, Orion will enter the atmosphere on a steeper trajectory, cutting exposure to peak heating from roughly 14 minutes down to 8. The goal is simple: less time for cracks to form. For future missions, NASA plans to change the manufacturing process entirely. Beginning with Artemis 3, the heat shield will be made more permeable, allowing gases to escape instead of building pressure. That assumption that the risk can be managed without changing the hardware is exactly what many experts reject. To critics, what happened during Artemis 2 was not routine wear. It wasn't an expected side effect of re-entry. It was a misdiagnosed failure. Much of the disagreement comes down to one word. NASA described the damage as char loss. Char loss is normal. It's the slow, fairly uniform erosion of material as heat burns it away. That's how ablative heat shields are supposed to behave. What Artemis 1 showed was something else. Large chunks didn't gradually disappear. They broke free. That process is called spallation, the sudden ejection of solid material caused by expanding gases trapped beneath a hardened surface layer. And spallation is not cosmetic. It's structural. The mechanism matters. In the skip phase, Orion grazed the hot upper atmosphere, then bounced higher, where it cooled off a bit. This gave heat shield gases made when super hot air cooks the protective Avcoat material extra time to soak deep inside, instead of escaping right away. When Orion dipped back into the atmosphere and reheated, those trapped gases swelled up fast like air in a balloon. You squeeze too hard. The pressure cracked the hard char layer on top, shooting out chunks like mini bullets from a rifle. That's spallation, and it's exactly what permeability is supposed to prevent. Here's where the controversy sharpens. While Artemis 1's heat shield failed because it wasn't permeable enough, the Artemis 2 heat shield is even less permeable. According to Dr. Danny Olivas, a former NASA astronaut and member of the independent review team, roughly 6% of Artemis 1's heat shield consisted of permeable material, and those areas did not crack. Artemis 2 has none. That change was made before Artemis 1 ever flew, before NASA understood that permeability was essential. Based on that, Oliva's conclusion was direct and unambiguous: it's going to crack. Even more troubling is how difficult this behavior is to predict. During re-entry, the heat shield's material properties were changing roughly every 20 seconds. That kind of constantly shifting state makes accurate modeling extremely difficult. Experts like Dr. Steve Scotty have noted that there was very little real-world data available to validate NASA's analyses. Dr. Charlie Camarda went further, calling NASA's reliance on procedural adjustments instead of design changes an unwarranted and foolish gamble. Yet despite this uncertainty, NASA chose to fly Artemis II with astronauts on board without another uncrewed test flight to validate the new entry profile. That decision has drawn some of the sharpest criticism. Opponents argue that if a private contractor discovered a failure mechanism of this kind, NASA would require a full retest before approving a crewed mission. Flying without one has been described as a clear double standard. Others point to the limits of mathematical models themselves. If simulations and ground tests were truly sufficient, they argue spallation wouldn't have appeared unexpectedly during Artemis I. NASA's confidence that it now fully understands the physics is seen as assurance built on incomplete evidence. Dr. Dan Rasky, a heat shield expert with 3 decades of experience at NASA, offered a stark way to frame the risk. Flying with chunks peeling off the heat shield, he said, is like standing at the edge of a cliff on a foggy day. You might not fall, but you're already at the edge. Even if the vehicle survives the loss of large pieces of protective material signals that the system has reached the point of incipient failure. NASA often points to one final safeguard, the composite structure beneath the avcoat. In What If We're Wrong tests, this structure was exposed to high temperatures for about 10 minutes and remained intact enough to protect the crew and allow a landing. But even supporters acknowledge that this structure was never designed to function as a backup heat shield. As Olivas has emphasized, its heat tolerance wasn't intentional redundancy. It was luck. For many observers, that reliance feels uncomfortably familiar. Critics draw parallels to Challenger and Columbia cases where known technical risks were managed procedurally instead of being eliminated at the hardware level, often under schedule pressure. In Artemis II, the heat shield wasn't redesigned. The flight profile was. That kind of workaround thinking, they argue, is exactly what spaceflight history warns against. Public frustration has grown as cost enters the picture. After nearly 2 decades of development, Orion has consumed more than $24 billion, roughly $30 billion adjusted for inflation. Discovering a fundamental weakness in a core safety component after that investment has been described as embarrassing, even by industry veterans. Concerns deepen when design consistency is considered. The Orion spacecraft for Artemis II and Artemis III are not interchangeable. Connection systems differ. Tunnels differ. Heat shield designs differ. NASA plans to fly 2 separate crews on 2 systems that have never been tested in the real world. Overlaying all of this is political pressure. NASA leadership has openly discussed the need to move forward quickly, to get up the hill rather than slow down. Critics worry that technical judgment is being shaped by schedule demands, budget scrutiny, and external expectations. For an agency whose reputation was built on caution after tragedy, that shift has unsettled many. And it sets up a comparison that's impossible to ignore. At this point, the debate around Orion stops being just a technical argument and becomes a philosophical one. Because NASA and SpaceX aren't just solving the same problem differently, they're answering a different question entirely. NASA's approach to Orion is built around prediction. The heat shield is evaluated primarily through computer models and ground tests. Real flights exist to confirm what the models already say. That isn't negligence. It's a consequence of cost. When each mission costs billions, flight testing becomes something you avoid unless absolutely necessary. SpaceX is structured around the opposite assumption. Dragon is tested in laboratories, but its real education comes from flying. Over 20 missions have exposed it to real re-entry environments, real thermal loads, and real failure modes. Problems aren't debated for years. They're fixed, flown again, and corrected further if needed. The difference isn't confidence, it's feedback speed. For NASA, models are authoritative and flights are validation. For SpaceX, flights are authoritative and models are support. That single inversion changes everything. Orion flies rarely because it must. Dragon flies often because it can. And when systems behave in ways designers didn't expect, as Orion's heat shield did iteration, becomes either an asset or a liability. Cost is what makes iteration possible. A Crew Dragon mission, including its Falcon 9 launch, typically costs a few $100 million. An Orion capsule alone exceeds $1 billion. A full SLS Orion lunar mission can reach $4 to $5 billion. Reusability compresses the risk. Dragon capsules fly multiple times. Falcon 9 boosters fly dozens. Each re-entry is another data point, not a once-in-a-decade event. Orion, by contrast, is largely expendable. Built for deep space endurance, long-duration life support, radiation exposure, and abort capability, it is engineered for survival, but not for rapid learning. The development histories explain why. SpaceX funded much of Falcon and Dragon internally using revenue to support small teams and fast iteration. When designs needed to change, they changed. Ownership of risk and schedule lived in the same place. Orion and SLS came from traditional government contracting. Fixed requirements, legacy constraints, and large prime contractors produced a system that grew heavier, slower, and more expensive with every revision. Over time, learning shifted from flight experience to paperwork. Before heading into orbit, every astronaut assigned to a space station mission goes through extensive medical testing and a mandatory isolation period. They also complete about 40 hours of medical training to prepare for emergencies in one of the most challenging environments imaginable: space. Even with all that preparation, not everything can be controlled. Unexpected situations still arise sometimes, forcing mission planners to make tough calls, including bringing a crew home earlier than planned. That's exactly what happened with SpaceX's Crew 11 mission. Launched on August 1, 2025, and docked to the ISS. The following day, the crew was set for an 8-month stay. But on January 8, 2026, NASA announced an early return due to a medical situation involving one crew member described as stable. The agency canceled all scheduled spacewalks, choosing to prioritize care on Earth over limited options in orbit. Crew 11 undocked on January 14, 2026 at 5:20 p.m. Eastern Standard Time and splashed down off the coast of California around 3:41 a.m. on January 15th. The early return, about a month ahead of schedule, marked the first medical evacuation from the ISS in its 25 years of continuous operation. That decision, though necessary, left a noticeable gap in station staffing. Expedition 74 was down to just 3 or 4 crew members for over a month. Normally 6 are needed to sustain full research operations, handle maintenance, and manage emergencies. With fewer hands, onboard science activities slowed, and workloads grew heavier for those remaining. To fill the gap, NASA decided to move up the next mission. Crew 12's launch date shifted earlier, likely to February 11th instead of no earlier than February 15th. While that adjustment helps the ISS regain momentum, it creates another challenge: timing. The new date overlaps with NASA's Artemis II mission, still targeting no earlier than February 6, 2026. That launch window runs from February 5th to 11th, with several possible dates, the 6th, 7th, 8th, 10th, and 11th. With both major missions sharing the same time frame, NASA faces a logistical puzzle. It's not yet clear whether Artemis II will still aim to launch before Crew 12, or if the agency will adjust the schedule to keep both programs on track. During the Crew 11 splashdown briefing, NASA's Jared Isaacman offered a clue about how the agency might handle the overlapping missions. He described Artemis II and Crew 12 as parallel efforts, meaning the two programs are developed and operated side by side, rather than one waiting on the other. That distinction matters. Artemis II relies on NASA's own infrastructure: Launch Complex 39B at Kennedy Space Center, the Vehicle Assembly Building, the Mobile Launcher Extensive Ground Crews, and the Deep Space Network for communication. Crew 12, meanwhile, is a SpaceX operation. It uses the company's pad at Cape Canaveral Space Force Station, SLC, 40 separate Falcon 9, and Dragon hardware SpaceX personnel, and mostly different tracking and communication systems. In short, different teams, different rockets, different launch pads. There's little overlap in the systems that would force one mission to stand down for the other. Each could, in theory, proceed within its own launch window. Still, parallel doesn't mean easy. Some shared elements stretch across both missions. First, ground resources and personnel. Even with separate facilities, several critical supports overlap. Navy and Air Force recovery teams, ships and helicopters that stand by in case of an emergency are needed for both launches. Certain weather officers, flight surgeons, and safety officials can't cover two major missions simultaneously. Security and emergency crews face a heavier workload when multiple human spaceflights occur within days of each other. Artemis II lead flight director Jeff Radigan pointed this out, saying there absolutely are constraints. He also noted competition for access to NASA's Tracking and Data Relay Satellite System (TDRS), which both missions depend on for live telemetry during flight. Second, range and safety zones. When rockets launch, air and sea regions are temporarily closed to keep people safe. The SLS rocket used for Artemis II requires a massive exclusion zone, while Crew 12's Falcon 9 uses a smaller one nearby. If those zones overlap or stretch too close together, only one mission can launch at a time. Third, weather problems can mess up the plan. February weather in Florida can be bad storms, clouds, strong winds. Artemis II has only a few try days in early February. If it gets scrubbed one day, it bumps into later days. Crew 12 is targeted no earlier than February 11th, 2026, so a bit later. But if Artemis II needs extra days or slips, it could push things around. SpaceX rockets are more flexible, they can try almost any day, but the big safety zone from Artemis II might block them for a while. It's a lot is happening at once. Artemis II is a historic first crewed moon trip in over 50 years, super important, and gets top priority. Crew 12 is needed fast because the space station only has 3 people right now after Crew 11 came home early for a medical reason. NASA wants a new crew there soon. Doing both in 1 month is like juggling 2 big tests on the same day, possible, but stressful, and needs careful planning. So what is NASA's solution? NASA's current approach is to keep both Artemis II and Crew 12 moving forward at full speed, but not to launch them at the same time. Administrator Jared Isaacman and Flight Director Jeff Radigan both agree that while the missions are developed and prepared independently, they should not share a launch day or even a tight overlap. The agency will continue advancing both in parallel until circumstances such as schedule slips or technical findings force a decision on which goes first. If that happens, Artemis II is more likely to shift, potentially to March, especially if delays arise from its wet dress rehearsal or from ongoing adjustments after Crew 11's early return. It's not prudent for us to put both of those up at the same time, but we have to ensure that both of them are ready to go, Isaacman said. We'll keep preparing both until one encounters an issue that pushes it back, or we'll have to pick one. And here is the deciding factor: the wet dress rehearsal. NASA's full fueling and countdown simulation. The wet dress rehearsal will determine how realistic a February launch is for Artemis II. The test could happen as late as February 2nd, leaving little room before the February 6th to 11th window. Launch Director Charlie Blackwell Thompson stressed that the results of that test will set the path we need to get through wet dress. We need to see what lessons we learn as a result of that, and that will ultimately lay out our path toward launch. If the rehearsal goes smoothly, she added, there are opportunities within February that could be achievable. NASA hasn't said exactly how long it would take to move from rehearsal to launch readiness. Acting Deputy Associate Administrator Lakeisha Hawkins noted that engineers will need a few days afterward to assess performance before deciding whether to roll and go, that is, stay on the pad and proceed directly into launch posture if conditions allow. Unlike Artemis I, this mission won't have to roll back to the vehicle assembly building if it misses the first launch window. Engineers added new work platforms to the mobile launcher so they can retest flight termination systems right at the pad. It allows us to stay out at the pad for 2 launch periods, said Blackwell Thompson. We'll get 2 launch periods when we go out. NASA leaders are also wary of what they call launch fever, the push to fly simply because of public or political excitement, especially with reports that President Trump might attend. Political pressure is one source of interest and enthusiasm around that mission, Hawkins said. But the agency is focused on doing the right and safe thing for the crew. John Honeycutt, chair of the Artemis II mission management team, underscored that safety remains the only priority. I think I've got a good eye for launch fever. I'm not going to tell the agency we're ready to go fly until we're ready to go fly. My one job is the safe return of Reed, Victor, Christina, and Jeremy, and that's a trust I intend to keep. For Crew Dragon, the situation is far more straightforward. After 5 years of continuous crewed service, the spacecraft has built a reputation for reliability and consistency that few vehicles in human spaceflight history can match. Since the first operational crew, one mission in 2020, SpaceX has established a steady rhythm. Between 2021 and 2026, the company completed 12 successful crew rotations to the International Space Station, plus several private missions, such as Inspiration 4 and Polaris Dawn. Across more than 20 total Dragon flights, including cargo runs, SpaceX has maintained a perfect human transport record, with no launch aborts, no losses, and no major in-flight anomalies. What makes Crew Dragon so reliable? First and foremost, reusability that works in practice. SpaceX has refined the art of reusing spacecraft safely and quickly. Some capsules have been turned around for new missions in as little as 137 days, demonstrating a mature process of inspection, refurbishment, and certification, a pace previously unheard of in human spaceflight. Next, proven escape and safety systems. The Super Draco abort engines have been tested and proven both in flight and on the ground, ensuring the crew's ability to escape a failing rocket. Those systems have never had to be used operationally, but their readiness adds a crucial layer of confidence. Third, reliable descent and landing performance. Crew Dragon's parachute system has succeeded in almost 100 test deployments, and every operational return has met its landing targets, whether splashing down off Florida or, most recently, off California. The Crew 11 re-entry, which took place on a condensed schedule, reaffirmed both the heat shield's durability and the vehicle's precision guidance during descent. Last but certainly not least, flawless docking record. Across more than 50 dockings with the ISS, the spacecraft has performed with precision, a testament to both hardware design and SpaceX's increasingly refined flight software. Vast is moving fast on Haven 1, its first space station, though the company has shifted its launch target from mid-2026 to the first quarter of 2027. The timing matters. NASA's next phase of its commercial space station program is expected to begin in 2026, and the ISS is due to retire less than 5 years from now. In that context, even a modest delay draws attention. But Vast's leadership isn't worried. In an interview with Ars Technica, Vast's CEO explained, "This is obviously our first space station, and we're moving as safely and as fast as we can. That's the date right now that we are confident we will meet. We've been tracking that date without slip for quite a while. And that's still a year, probably 2 years, or even more ahead of anyone else. It will be building the world's first commercial space station from scratch, from an empty building, and no team in under 4 years." That confidence has roots in real progress. Haven 1 has entered early vehicle integration, moving from structural completion into the first phase of system integration. As of January 10th, the team has completed the primary structure and part of the secondary structure, with all structural acceptance testing finished last November. These milestones confirm that the station's pressure vessel and core structure meet their design and safety standards. The project is now in clean room system integration. Phase 1, which focuses on the installation of thermal control and propulsion systems, pressurized fluid lines and interior structures, along with pressure and leak testing as each system is added. In practical terms, Haven 1 is no longer just a structure, it's taking shape as a functioning spacecraft. the next major step. Phase 2 integration in mid-2026 will bring in the avionics guidance navigation control systems, air revitalization, and life support hardware, the core technologies that will give the station its operational capability. VAST expected to complete vehicle closeout by fall 2026. By late 2026, the final phase will add crew habitation components, micrometeoroid and debris shielding thermal radiators, and solar arrays, completing the vehicle ahead of launch preparations. Following that, Haven 1 will move through full environmental testing campaign at NASA's Neil Armstrong Test Facility, formerly known as Plum Brook Station in Ohio, including vibration thermal vacuum and acoustic trials. If all goes to plan, Haven 1 will be ready for launch in early 2027. This places VAST ahead of where many first-time space station programs tend to stall, and puts it on a credible path toward flight, as long as system integration and Plum Brook testing stay on schedule. Most early station projects hit trouble in one of two familiar places. The first is before a real spacecraft ever exists. Designs look solid on paper, mock-ups are impressive, but a fully tested pressure vessel never materializes. Programs fade there not because the idea was bad, but because feasibility was never truly proven. But the more difficult choke point comes later, right after the structure is complete. That's when a design stops being a collection of parts and starts becoming a single functioning spacecraft. It's the stage where plumbing, wiring, and thermal systems must all fit and operate together exactly as planned. Small mismatches here can snowball into major redesigns, retests, and months of delay. Many first-time programs lose momentum at this transition, not from lack of ambition, but because the complexity of integration becomes too costly or too slow to fix. VAST appears to have cleared that hurdle. The primary structure is finished, acceptance testing is done, and clean room integration has started. Those steps confirm two important things: the design was mature enough to build, and the interfaces between systems were defined well enough to start real hardware installation. In other words, the program didn't stall where so many others have. That's why calling it ahead of where many first-time station programs stall isn't just optimism, it's an accurate description of progress. Part of the reason VAST has reached this point lies in lessons drawn from earlier successes. Programs like the ISS China's Tiangong and NASA's Gateway all survived this same transition by doing a few things right. They locked in their core designs, early preventing constant midstream changes. They followed a proven assembly sequence, installing cooling and fluid systems, first propulsion, next interior structures after that, and only then adding avionics and life support hardware. That order matters because pipes and thermal lines define the available space. Everything else must fit around them. And from the start, they designed for the full range of environmental tests, vibration vacuum heat, and acoustic loads expected at major facilities like NASA's Plum Brook. VAST is also learning from the mistakes of its predecessors. The company took a different approach with Haven 1 to avoid the cost complexity and management challenges that shaped the ISS. One of the biggest lessons from the International Space Station is the downside of its modular design. The ISS is made up of many connected modules, each with its own docking systems, seals, and structural joints. Those countless interfaces create potential leak points and drive up maintenance costs. Its truss system and core connection nodes are so interdependent that replacing them would mean dismantling large parts of the station itself. Building something that complex also requires years of international coordination and dozens of launches. For a first-time commercial team, that level of risk simply isn't practical. VAST took a different path. Haven 1 is a single self-contained module that can be launched in one flight. That eliminates the need for on-orbit construction and sharply reduces the number of possible leak points. It also saves enormous cost compared with the 35 launches it took to assemble the ISS. Every part of Haven 1 is built, tested, and verified on the ground before it ever reaches the pad, simplifying management and greatly improving reliability. At first, Haven 1 might seem small. Its pressurized volume, about 100 cubic meters, is only a fraction of the ISS. But that size is intentional. Haven 1 isn't meant to replace the ISS on its first day. It's meant to prove that VAST can build and operate a crew-ready station safely. That space is enough for short missions with a small crew. Each mission is planned for roughly 2 weeks, 10 days on the station, and 4 in transit, but the design allows for stays of up to 30 days if needed. The entire station weighs around 15 tons, small enough to ride on a single Falcon 9. Keeping it compact has real advantages. Less volume means less air to manage smaller life support systems and lower power and cooling needs. Every cubic meter you add in orbit multiplies complexity, mass, and cost. By staying small, VAST can focus on performance reliability and learning fast before scaling up to something larger. VAST is also rethinking how to keep a space station financially and operationally sustainable. Instead of recreating everything from scratch, the company is building Haven 1 around existing infrastructure that already works. A big part of that strategy is its partnership with SpaceX. Haven 1 is designed to lean on the Dragon spacecraft for several essential systems. The two vehicles operate together as a single connected environment. For example, Haven 1 doesn't carry its own restroom or emergency return systems. Those are provided by Dragon. The spacecraft also backs up life support and serves as the crew's launch and return vehicle. By depending on Dragon for these core capabilities, VAST can keep the station lighter, simpler, and far less expensive to operate. That same focus on efficiency extends to the company's business model. The ISS costs NASA roughly $3 to $4 billion every year just to stay operational. VAST's approach is meant to avoid that trap. Haven 1 is being developed to serve a range of users: government research programs, private research groups, small manufacturers, and even individuals or teams with specialized goals in orbit. VAST is already in talks with international partners and has opened an office in Japan to reach clients across Asia, Europe, and the Middle East. The idea is not to sell short tourist trips, but to give customers the chance to carry out meaningful work in orbit. Those who need lab access can bring their own equipment, operate it themselves, and reduce overhead costs in the process. By keeping management in private hands, VAST expects to run operations more efficiently than a government-led station could. The company also sees Haven 1 as a platform to help unlock what many call the orbital economy. With crew power and facilities already in place, the station could support in-space manufacturing fields like semiconductors, fiber optics, and pharmaceuticals, where microgravity offers unique advantages. Haven 1's development follows a phased test-and-learn approach. Rather than jump straight to building a massive station, VAST is using this smaller outpost as a proof of concept, a place to gain hands-on experience before scaling up. Lessons from Haven. 1 will feed directly into Haven 2, a larger, more flexible station planned for launch on SpaceX's Starship. VAST calls its development process fly, fix, repeat. It's a philosophy borrowed from the faster iteration cycles of modern aerospace companies. Typically, SpaceX designed to evolve the hardware with each mission instead of locking in designs for decades. Haven 1 will also test something no human-rated space station has yet demonstrated: artificial gravity. By rotating the entire vehicle during uncrewed operations, VAST plans to study how partial gravity affects spacecraft systems and eventually human health. It's a small but significant step toward solving one of the biggest challenges in long-duration spaceflight: the toll of zero gravity on the body.